Okay, so like I said, Unit 1, Energy and Rates, Chapters 5 and 6. Again, it's in the middle of the book because I like to start with something that has got some calculations and actually does relate to what we've done in the past. That's why we've kind of jumped ahead to this location. So, like I said, at this point, it's definitions and discussion on terms that are associated with what we call thermochemistry. Okay, thermodynamics. This entire unit is about heat and the way heat moves and behaves. That's what the first part of this unit is on. And the second part is applying that knowledge of how heat moves and behaves to chemical systems. All right? We already have, and when I say we, I mean you guys, I'm sure you all have an intuitive sense of the way heat behaves, and that's because in your everyday experiences you deal with your own temperature. Our bodies have a temperature, and if you have a net heat gain in your body feels warm, and so you know that you intuitively want to dissipate that heat, so you take off the sweater and you cool down. All right. And right there is a fundamental law of thermodynamics. Hot things will transfer heat to cold things, all right? And that's what's happening when you take your sweater off and you cool down. Your warm body, which has an excess amount of heat energy, automatically, you don't even have to think about it, it's just the way nature works, that heat gets transferred to the surrounding air. The same thing happens to your cup of coffee. If you got a coffee in the morning, it's nice and warm, you leave it, you forget about it for a half an hour, you come back, it's cooled off. So hot things automatically transfer heat to cold things. This falls under something called the zeroth law of thermodynamics. You might be wondering why there's a zeroth law of thermodynamics. There's actually two main laws of there are three laws. The zeroth law, the first law, and the second law. And you might say, why did they put a zeroth law? Why not 1, 2, and 3? The first law, which I'm going to talk about in a moment, was actually the first law that a scientist kind of proposed. This is the way heat or energy and heat behave. Boom, the first law. And then the second law came along, and it deals with something else called entropy. We'll talk about that a little later on. And then someone realized, hey, there's something more fundamental than that first law. There's something even more underlying. And that's the idea that heat automatically goes from warm things to cold things. And therefore, they had to kind of backtrack and call it the zeroth law to put it in front of the first law. And because those other two laws were kind of entrenched there, they had to kind of backtrack and call it that. So thermodynamics is the study of energy and energy transfer. And it's not just all energy. It's not just gravitational energy and kinetic energy, which you may have learned in physics. And we're going to be using those terms. But we're talking about heat energy, obviously, and that comes from the prefix there, thermo. Dynamics means to move, so thermodynamics is energy moving or energy transfer. Now, if we apply the laws and the ideas of heat energy transfer, which I'm going to teach you, if we apply that to chemistry, and we then look at what's happening energetically in a chemical change or a physical change, and when I say physical change, I mean melting or boiling, or a nuclear change, because we can include those nuclear reactions. We've talked about them last year. Remember, we talked about alpha decay and beta decay and a little bit about fusion and fission, just a little bit. We can analyze those things in terms of how much energy is entering or leaving that system when these changes take place. So that's what thermochemistry is. And that's ultimately what we want to do in this chapter. So let's talk then about some of the terms that we need, and that is energy. So like I said, today is going to be lots of definitions. If you've taken the physics, grade 11 physics, that's all you really need here. You'll do a unit on energy in the grade 12 as well. And you've probably seen that definition in the past, the ability to do work. And then we have to define work, because when we say work, we don't mean going to your job. A physicist, when you're dealing with work, means that it can apply forces on things and cause things to move. That thing about the same direction as the applied force, blah, 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 that's a very physics idea. We're not really worried about that, but I had to put the right definition down, not just kind of a watered down. That's what the definition of work is. So there's many types of energy, and we'll define those. Actually, I was going to show you some things here, but we'll wait till we get to the definition of those different types of energy, because they are going to come up. Energy is measured in joules. All right, joule. The unit joule is in honor of James Prescott Joule, who did a lot of work. There's a lot of work. He did a lot of scientific investigation concerning how gravitational objects, things that are falling down. What he actually had was in his room at the university, because he was at a university, he had a pulley system that had a big mass on it, and then that pulley was attached to a kind of a spiral or that has all the rope wrapped around it, which was then attached to an axle that had these paddles on it. And he submerged the paddles in water, and then he took the temperature of the water, and then he let the mass fall down, and as the paddles turned, they stirred the water up, and then he noticed that the temperature of the water increased because the water was all stirred up, and he was able to calculate an equivalent of gravitational energy converted directly to temperature or heat energy. He was the first one to actually quantify how regular forms of energy that we talk about, kinetic energy and gravitational energy, can be converted directly into heat energy. Really opening this idea of, oh, okay, heat is a form of energy. It's just, what happens after all of these other energy forms kind of are done doing their stuff. We end up with heat in the end. So that really opened up the world of thermodynamics. A joule, technically, if work is equal to force times distance, is a Newton meter. All right, so it's an aggregate unit. It's got multiple units in it. A Newton, again, for those who are taking physics, force is equal to mass times acceleration, right? And that's newtons. So that's a kilogram, and that's a meter per second squared. So a joule is technically a kilogram meter times meters per second squared, which makes it a kilogram meters squared per second squared. All right. You don't need to know that in this course, but it does come from our basic units of length, time, and distance. Most of our units can be converted into that. All you have to know is that they are joules, okay? Joules are quite small in terms of energy amounts, so very often when we do our calculation, we end up with thousands of joules, so we'll convert it to kilojoules, and sometimes we end up with millions of joules, and we just convert that to megajoules. We just use our powers of 10, all right? Okay. Now I'm hoping you've all seen this law before. The law of conservation of energy. You know, if I was teaching grade 11 physics and I was introducing this, or maybe even to the younger kids, I would say, this doesn't stand for turn the lights off when you leave the room, because electricity costs money, right? Your parents, turn the lights off when you leave the room. What do you think, I'm made of money? That's not the law of conservation of energy. That's like conserving electricity or something. You've seen conservation laws before. There are fundamental laws of our universe. In chemistry, we have the law of conservation of mass. In a chemical reaction, the mass before, or of the reactants is equal to the mass of the product. That's actually a form of this law right here. This is actually a more fundamental version of it. Energy can neither be created nor destroyed. That's one way of saying it. You can't have energy just come out of nowhere. It has to have an origin of some sort, some other form of energy. That kind of has some significant meaning in terms of our entire universe and things like the Big Bang Theory. That means that in Big Bang Theory, that's funny. Anyway, no, I'm not talking about the TV show. I'm talking about the actual Big Bang Theory. And if our universe was created from this small, dense, energetic starting point, then all that energy that was in that starting point has to be the energy that we still see here today, because the energy couldn't come from anywhere else. All that energy was there. Now, what's happening to that energy? It's just kind of spreading out. It's just kind of getting thinner. All right? And that kind of goes with hot things get cool. That hot, dense core is slowly spreading out that energy as the university grows and its things are cooling off. It can be transferred from one form it can be transferred from one substance to another and can be converted from one form to another. All right? I'll talk about gravitational and potential in a moment. So this is the first law of thermodynamics. The law of conservation of energy is the first law of thermodynamics. Energy of the universe is constant. Okay? Now let me just write this in a slightly different form. This means here that the change in the energy of the universe is zero. Delta, that symbol right there, means change. Have we seen that before? Have you seen a delta before? Now I'm kind of short on room here, so I'm going to write it above, but you can write this below. But delta means something like E2, right, the final energy, minus E1 equals 0, right? Because we've all seen change as a symbol, right? It means final minus initial. And I can rearrange this guy as well. I'll put it over here. It means that the E2 of the universe is equal to the E1 of the universe. Okay? It means that the energy is always the same. It doesn't matter what point in time we choose. There's also another very important meaning that goes along with this. If I have and this is going to be a tricky one to kind of talk about and explain. If I have one system changing in energy, one thing that loses energy, then that means the other system that's nearby has to gain energy, and that's my coffee cup situation. So let's say here that I've got a coffee cup. I don't think you necessarily want to draw this quite yet, and it is hot, right? This thing has a high temperature, all right, and it loses some energy. It changes some energy, delta E. Then the surroundings, whatever that is, we can call that the air, right? The air. It means that that air has to gain that energy that was lost, and it's exactly equal to it. Whatever one thing loses in energy, the next thing has to gain that energy. So we have to always account for the energy, and that's what allows us to do our calculations in thermodynamics. For every joule that one thing loses, that neighboring thing has to gain all that energy, the exact same amount of joules. So that change in energy becomes very important. Okay, let's talk about the types of energy that we can be dealing with. In other science courses, you may have talked about energy, and you may have talked about all the different forms of energy. Kinetic energy and potential energy definitely come up. Kinetic energy, usually the first type of energy you talk about and learn about. And then in terms of potential energy, you learn about all kinds of different types of potential energy. And you would probably list them all. You know, that's a classic test question. List the types of energy. When it really comes down to it, though, you really only have kinetic energy and potential energy. And then light is carrying some energy too. Light carries energy with it as well. You could argue that as being a form of kinetic energy because the light is moving along through space. Let's not worry about light at this point in time. But when it comes right down to it, you really only have two forms of energy. Kinetic, something's moving, or potential, something's attracted to something else, thus giving it the ability to move. In the end, all forms of energy, all forms of potential energy will be converted eventually into kinetic energy. Kinetic energy, the energy possessed by objects in motion. There's the equation. We're not going to be using that equation directly. This is only for people who've taken physics to recall the fact that there's that mass and velocity relationship. Potential energy, stored energy, energy that can be released or harnessed to do work, energy that a body possesses by virtue of its position, and it's also got to have a secondary part to it, its position in what we would call a force field. There has to be a force between those two things that are relatively positioned with each other in order for there to be potential energy. Classic example, gravitational potential energy. That's what the first one is. You'll notice I just write EP because I'm really not going to be designating the difference between gravitational potential energy and electrostatic potential energy and magnetic potential energy. That's for a physics course. Here, I just want you to think of potential energy, stored energy. Water held behind a dam possesses potential energy. I don't have water near, well I do, but I'm not going to use water, that's messy. I've got my collision card here. I can hold that collision card up, all right? There's a force of attraction between the collision card and the earth, and that therefore has the cart kind of being pulled towards the earth. If I were to let that go, it would convert into kinetic energy, and it could do some work. It could land on my toe and work on my toe and cause some damage, all right? So, gravitational potential energy. In this case, bonds holding carbon atoms in coal together. All chemical bonds are a form of electrostatic potential energy. Now, electrostatic potential energy is that electrostatic force that we talked about last year, of the force between opposite charges. So the nuclei and the electrons of the carbon atoms are mutually attracting each other. They form a covalent bond, and therefore they're pulling together due to these electrostatic forces, and that contains potential energy right there, all right? They're actually pulling together, and if they get too close, the nuclei will repel each other, and they'll push each other apart, and that's why we have this nice bond where they're not too close and not too far, and we get this stored energy in the bond. That's electrostatic potential energy. We could have magnetic potential energy. If I had some magnets here, right? If I pull these two apart, I hold them at a distance away, there's magnetic potential energy there. I can let it go, it snaps back. There's nuclear potential energy. In the nucleus of an atom, there's attractions between the protons and the neutrons called the nuclear strong force. There's repulsion between the protons because they're both positive. That's a potential energy situation. There's a lot of potential energy in a nucleus, which is why when a nuclear reaction takes place, say in a nuclear power plant, and that nuclei breaks apart and moves away from each other, so much energy is evolved. It's given away. But again, it's a form of potential energy. And so essentially, we've got potential energy in a system, and we've got kinetic energy. I could set up an example of that. Here I could give this cart some potential energy, and it could do some work, and it could transfer that potential energy to the next cart. If I wanted to make this look a little more like an atomic situation, not only do I need a repulsive situation, but I need a bond in between it. I need an attractive force. I don't know if this is going to work. I just made this up this morning. We'll see what happens. If I attach my spring here, right, and I put it over onto this one, and that's not great. Let's put it a little closer. Let's see if we can get a little closer here. Put it around here. I'm going to wreck my spring, but that's okay. Yeah. There we go. Perfect. So now I've got these two carts. They're kind of attracted yet pushed away. And I can give it some energy here. And you can see there that there's that attractive force and that push away. And so when I do that, I've got the carts moving back and forth, kinetic energy. There's the spring stretching or compressing, potential energy. And so I've got this mixture of the two energies in this system. And that's going to be the case when we talk about a chemical system. The chemicals can be moving. We know that from the kinetic molecular theory. They can be rotating. They can be vibrating. They can be translating along. And they can also have that attractive and repulsive force of potential energy in it. So a chemical system will contain both kinetic energy and potential energy. So now let's apply it to heat, thermal energy. So thermal energy is the total kinetic energy available in a substance as a result of the motion of its particles. So thermal energy is kinetic energy. It's much different than the kinetic energy of my carts, and it's also much different than the kinetic energy of, say, a car driving down the road. Thermal energy is the kinetic energy of molecular, atomic-sized objects vibrating due to heat, being heated. In my cart situation, you'll notice the kinetic energy eventually dies away. Oh, now it doesn't even work. That's no fun. That's not bad. The kinetic energy eventually dies away. Where does that kinetic energy go? It goes into the friction of the table, and therefore it ultimately heats up the particles and they start to vibrate, and it's converted into thermal energy. So the large movements of a large macroscopic object, the kinetic energy, eventually goes into the kinetic energy of all the little particles, and things heat up. All right? Again, that's the law of conservation of energy. All of this kinetic energy and spring potential energy that was in this macroscopic object eventually go into heating up the desktop a little bit, and then that gets spread out through the desktop and into the air, and everything kind of just gets a little bit warmer because of all the energy that's been added to it. Thermal energy depends on the total number of particles, so the more stuff you have, the more thermal energy you have. That's essentially a statement of if you have a cup of water at 50 degrees Celsius and you have a hot tub of water at 50 degrees Celsius, there's more thermal energy in the hot tub because there's more particles, and therefore there's more in total kinetic energy. All right. So thermal energy, we're talking about the kinetic energy of the moving particles. So now the term heat, and this is going to become probably the most important term of this unit. Because it's very difficult for us to know, well, no, that's not true. We can know the exact amount of thermal energy an object holds. But in many cases, we're not concerned with that maximum amount of thermal energy an object has. We're more concerned with how much energy has been transferred to that neighboring object. I already talked about, if you're too warm, you take your sweater off, and then some energy is able to leave, and you feel cooler. That movement of energy is what we call heat. That becomes a very important thing when it comes to things like insulating a house. You want to prevent the energy from leaving, so you want to stop that heat transfer with insulation. So heat is the movement of thermal energy from one object to another. In the field of biomechanics, if you were to be studying athletes and the way they use chemical potential energy in their bodies and how efficient they use it at, you would do experiments where you would measure how much heat is coming off of that athlete as they're performing whatever they're doing. It's a tricky thing to do, right? You actually have to almost get them into a pool of water so that they can do what they do, so that that heat can be transferred out of their body and then caught by the water, so that you can then measure, just like Joule did, what the water is doing in response to that. And so that movement of thermal energy from one object into a neighboring object is heat. and that's something that we can measure in the laboratory. We're going to learn how to do calculations to measure heat transfer. What that then allows us to do as chemists is to do a chemical reaction in some water so that the chemical reaction maybe produces some thermal energy and then transfers its heat to the water, and then we can measure that. So heat is one of the most important things in this unit. We'll be learning an equation on how to calculate it, and we'll be using it quite a bit. A very important aspect of something obtaining heat is that its temperature changes. If that athlete is working in the water or our chemical reaction and that heat is transferred to the water, the temperature of the water will rise. It will now have more thermal energy. It's that temperature change that we can measure that allows us to do this. So temperature is a very important thing. And it's the average kinetic energy of the particles. You add heat to it, all the particles move a little faster. That average kinetic energy, we call that temperature. And we can measure that with a thermometer. All right, so heat, very important. The transfer of thermal energy. And temperature, that's the average kinetic energy. It allows us to measure the heat transferred. Okay, so we've got all of our terms now. We're ready to start really thinking about how we can then start measuring the movement of energy, because that's what thermodynamics is all about. It's about energy moving. So I've just told you a couple of examples on how scientists, depending on what you're studying, could study how heat is transferred from various objects. I gave you the example of the athlete doing their thing, maybe in a container of water, so that the heat produced by their body could be transferred to the water. I've also talked about a chemical reaction, just in general, how a chemical reaction could be done in some water, and then we could then have the heat produced by the chemical reaction go into the water. Now we have to define some of these things in these experiments I've been kind of getting you to think about, and that is, we need to call one part of it the system, what we're studying, in this case a chemical reaction, and the thing that's collecting the heat for us, the surroundings, in this case the water. Now it doesn't have to be water, but in our class all of our experiments will be done with the surroundings as water. We're going to do reactions so that they can produce some heat or absorb some heat, and they will transfer that heat to the surroundings or absorb that heat from the surroundings. All right? So, a chemical system. The reactants and products under study as represented by the chemical reaction. So here we've got a chemical reaction. This is just some magnesium reacting with some hydrochloric acid to produce some magnesium chloride and some hydrogen gas. And we've seen that reaction before. I'm not going to show it to you, but we've seen it bubble. It produces lots of bubbles. We did it with zinc. I filled the helium balloon with that, and it actually gets quite hot. Now, let me just draw a little picture to represent the system and the surroundings, just to show you the difference. The surroundings are the matter surrounding the system, which is capable of absorbing or releasing the thermal energy. So this is the thing that's going to either get hotter because it's gaining in energy or get colder if it loses energy. Let me just draw a picture of it here for a moment. And this is, you might think, well, why would you draw a picture, Mr. Sanders? This is pretty plain. Let's say that we did this experiment in a container of some sort, and let's just say it's a beaker, and I'll just draw a beaker here. All right. And, oh goodness, might be pretty bad. And let's put some water in that thing right there. So we've got some water, and I'll just put a little label here. Obviously, that's H2O. And inside this, we've got some hydrochloric acid. So in other words, we've dissolved hydrochloric acid in it. So we've got some HCl in here, and then we dump some magnesium in it. So we dump some chunks of magnesium in there, all right, and I'll just label those as Mg. And what's going to happen is they're going to bubble away. I'm running out of colors. See if I can come up with a new color here. Oh, bubbles must be pink little things, and it won't let me do that. That's unfortunate. That's no fun. We'll make the bubbles little yellow dots, and it bubbles away, and the bubbles rise to the top. Okay. And in the end, we end up with a little bit of MgCl2, which dissolves away, and then we've got the H2 that's bubbling away. Okay. So, what's happening here? We've got the chemicals inside the water. They're reacting away. They're becoming products. They give off some heat. And where does the heat go? The heat goes into the water. Now, you might say, oh, but isn't that just like your coffee? Wouldn't the heat eventually end up leaving the water and the cup and going into the air? And that's a true statement. It would. Ultimately, that heat's going to spread itself out. But as chemists, we want the water to catch all the heat. We don't want the heat to escape. So when we talk about surroundings, it turns out that the water in here are the surroundings. We want the water to catch all the heat. In here, the reactants and the products are what we call the system. That's the thing that we want to study. If the water's the surroundings, then what's the outside of the beaker going to be called? What do we call the air and the desks in the room and the scientists that are doing the work? Well, they don't really have a name. I call them the surroundings. But they're not what we want to study. We really don't want the energy to escape from the water because we want the water to catch all the energy so that we can measure it. In reality, that's not possible. In reality, the zeroth law of thermodynamics is going to cause that energy to escape into the air. So we want to build a device that keeps the heat in the water as long as possible so we can catch that heat. So when I say the system, I'm talking about the chemical reaction. And when I say the surroundings, I'm talking about the substance that's around the chemical reaction that's going to catch the heat, in this case, the water. The rest of us sitting out here outside of the beaker are in the surroundings, and we really don't want the heat to go there, even though it's going to. So the trick is to build a special container that keeps all the heat in the surroundings. Now that makes no sense. I just said keep the heat in the surroundings. But we need to get over that. Surroundings are the thing that's catching the energy. In this case, it's the water. Okay? So let's talk about how we can keep the heat in the surroundings, which seems a little odd, but that's exactly what we need to do. Let's head back to the PowerPoint, and let's talk a little bit about, before we get to that, we'll define a couple of things here. So the system is the thing under study. In my other example of the athlete working out and trying to determine what their energy output is, the athlete would be the system. The athlete would be the thing you're studying. If a system, chemical or athletic, An athletic system, that's funny. If the system transfers heat out into the surroundings, we say it's exothermic. I've used that term before. I would have mentioned it to you, I can't remember what unit it would have been in, but I'm sure I would have mentioned that term to you before. Exo means to leave, thermic is heat energy. These are all, I'm pretty sure, Greek prefixes and that type of thing. Exothermic, the system loses energy. The temperature of the surroundings increases. Combustion, freezing, condensation. I've got combustion twice. I don't know why. Nuclear fission and fusion are all exothermic. If you put your hand too close to the fire, your hand becomes the surroundings. The chemical reaction of the system is exothermic. It transfers energy to your hand gets hot, you get burnt. It's exothermic. As human beings, we can easily test whether something is exothermic or endothermic just by touching it. If you touch something that is hotter than your hand, then automatically, due to the zeroth law of thermodynamics, the energy will transfer into your hand and it will feel hot. It's exothermic. It's transferring energy to your hands. Right? Pretty straightforward? All right. Freezing is actually an exothermic situation. It seems a little strange that freezing would be exothermic, but when water freezes, the motion of the particle slows down such that it's moving slower and vibrating in a solid structure, and that gives energy off. When you grab an ice cube, you're actually not feeling freezing. What change of state are you sensing when you grab an ice cube out in the air? Melting. And melting is the opposite. Melting is endothermic. When a solid piece of ice, which has very low vibrational energy, gets in contact with your skin transfers energy into the ice. That causes the particles to vibrate and melt. In order to sense the exothermic of freezing, you'd have to have your hand in the water in the freezer as the ice was freezing. I'm not trying that. That has to happen at 0 degrees Celsius, which means your hand also has to be at 0 degrees Celsius. And because your hand is made up of mostly water, not only will the ice be freezing, but your cells will be freezing. And I'm pretty sure cells don't like that. Not most cells. Some frogs can be frozen and you can thaw them out and they'll jump away. But I don't think human hands work that way. It would be interesting though, could you, if you did, as it was freezing and you were feeling extreme pain because of frostbite, would it give some energy to your hand for a brief moment as it froze? And it still hurts. I don't know. I have no idea. Could you do that with another substance? I suppose if you had a substance that had a freezing melting point that was, say, at 30 degrees, would it work? Actually, I believe gallium, is it gallium? Gallium melts and freezes at 29.8. I've seen it where, I've only seen pictures, but you put a piece of gallium in the palm of your hand, 32 degrees is your skin, your body temperature, it melts in your hand. Would it feel cool as it melts? I don't know, I've never done that. That'd be neat. Could you stick your hand in some liquid gallium and cool it down a little bit? Would you feel a little bit of heat as it freezes? I don't know. I do know that there's a technique used by farmers that farm things like oranges and tobacco. I don't know what tobacco is. Anyway, the tobacco farmers I know do this. I used to work on a tobacco farm. And if it's going to freeze, they spray water on the plants. So if it gets down to freezing, the water freezes, and the idea is that it might protect the plants. If that, in that freezing transfer, does it warm the plants up? They've been doing it for many, many years. They still do that. There must be something to it. So, melting is endothermic. Energy has to go in to melt those things. Vaporization is endothermic. Breaking chemical bonds is endothermic. If you want to break a bond, you got to put energy into that thing, right? Here I've got a situation. If I want to break that bond, I got to put some energy in it to break it apart. So we're going to then be transferring this idea to chemical bonds, obviously. Okay. So let's now talk a little bit more about systems. Do I have pictures with this? No. Now, we are so, as chemists, we are so handcuffed by the terms that this is where it gets, it can get a little confusing, but we'll take our time through these last definitions to keep things straight. I'm going to draw a couple of pictures here beside them, so if you want to leave a little bit of space for some doodling there, you can do that. Do the beaker again. Beaker of some hydrochloric acid. It's got water in it. It's got HCl, Mg, and we're going to get all kinds of bubbles, and the bubbles are going to escape. That's bubbles escaping. I don't know how you can see bubbles escaping, but once the bubbles break, it becomes gas and it escapes. All right? Just like before, if I'm defining a system and surroundings, my water is still the surroundings, and my chemical reaction is still the system. And actually, I will call it the system, all right? And the reason I want to call it the system or the system is that this term up here, system, does not describe the chemicals I'm studying. It describes this entire setup that I'm using. The fact that there's no lid on it, it's open, all right? It's unfortunate that we use the term system again. The term system in this case means the system of apparatus that we're using to study something. It's not the system, the chemical reactions, okay? This case, it's an open system because I'm not catching anything, and all the bubbles can leave, and the heat can leave, and I really can't study anything about this, except that it makes bubbles. The only thing I can get conclusively is that, ooh, it makes bubbles. That's a grade 9 observation. Okay, let's put some magnesium and some hydrochloric acid. What do you see? Bubbles. It's a clear, transparent, actually I can't say that. It's a colorless, transparent liquid, and it's got a gray solid. You remember the good old days? And it makes bubbles. Yeah, that's a single displacement reaction, right? And if I'm studying the single displacement reaction and then it makes bubbles, that's great. But if I want to study the law of conservation of mass, this is unacceptable. Why can't I study the law of conservation of mass with this experiment? Yep, I'm losing the bubbles. So I can make qualitative observations using an open system, but I can't learn anything about what's going on in that system, the chemicals I want to study. Because not only are bubbles leaving, but what else is leaving? What have we been talking about all the way through? Heat, no good. Open system, no good for us. A closed system, one in which only energy can move in and out, but matter cannot. So how do I turn this into a closed system? I put a lid on it, and I keep the bubbles from leaving. So again, I've got H2O. That's still my surroundings. I've got Mg, I got HCl, I got H2, and I've got a bunch of H2 up here. H2 in that space. It didn't leave. And then I've got some MgCl2, and that's a closed system. But it's just made out of glass. So some sunlight can come in, some of that thermal energy can get out of the glass, the heat can escape. I could study the law of conservation of mass with this one if I wanted to do the good old grade 9 lab where you put the thing in the Erlenmeyer flask and you put the stopper on it and you put it on the scale and you write down the mass and then you cause the chemical reaction. Sometimes some teachers do this. Do you do that one? You put it back on the scale and it's the same mass and you go, it didn't change. Was it not supposed to change? Grade 9 teacher, yeah, it was supposed to change. Well, that's kind of dumb, isn't it? It's a conservation of mass. Would you just sit down? It's an important theory. Man, the grade 9's driving me crazy. Anyway, you could study the law of conservation of mass. Not very exciting, except to Antoine Lavoisier. I'm sure he thought it was pretty exciting. So what do we need? We need an isolated system. We need something that not only keeps the matter in, but it also keeps the heat in. And due to our oh so expansive budget that we have at a high school, let's see if I can find them where to put them. What did I do with my calorimeters? This is unacceptable. Well, I'm going to need them in the next week or so. Rats. I'll have to find them. I'll find them. We use styrofoam cups. That's going to keep the heat in. Not. But it does a little bit. But some of it's going to escape. If you have coffee in a styrofoam cup, it still feels warm. Error analysis. Heat escaping. Going to prevent us from keeping all the heat in. But it's not bad for what we're going to be measuring. And by the way, if you use heat escaping as an error, buying high-tech styrofoam cups is not a good fix, right? We've had this discussion. Get a high-tech scale. That's always funny. All right. So we try to prevent the energy from leaving. And you know what? That's the tricky thing that chemists have to deal with, coming up with a proper way of keeping that heat in. And you never can keep it all in. Everything cools down in the end. So when you do an experiment, you want to measure quickly, because the longer you wait, that heat starts to leave. So it's an isolated system that we want to study. I could label this up. You could say, here's the water, the surroundings, they're in there. Here we've got some magnesium and some hydrochloric acid, and we're going to catch all that stuff. That's the system, and we're going to measure it. Okay? All right, so we're going to use isolated systems. and that is some questions that just deal with this idea of heat and, what's the matter? Did we get that down? We're good? Just some practice problems that deal with it. Like I said, today was not going to be very exciting. We have to just get into our minds this idea of the fact that we've got kinetic energy and potential energy. And we've got then thermal energy, the kinetic energy of the particles. If that thermal energy is transferred to something else, we call that heat. That's the very important thing that we're going to be doing, because we can measure that. How do you measure heat? You measure the temperature change. If I measure the temperature of the water before and the temperature of the water after, I can do some calculations and figure out exactly how much heat it's gained. And due to the first law of thermodynamics, if I know how much heat the surroundings gained, where did that heat have to come from? If the surroundings, i.e. the water in my coffee cup calorimeter, if my surroundings get warmer, where did that heat have to come from? What do we call that? The system. That had to come from the system. Because we can't look at the system. We can't just say, all right, if just by staring at the reaction of magnesium with hydrochloric acid, I can't get information out of how much heat that's going to produce. That tells me nothing. It's unfortunate, but we cannot get into a magic school bus, fly down to the magnesium atoms, look at the way they're behaving in order to figure out how much heat it's going to produce. I can't do that. You cannot look at the system with our senses. So the only thing that we can do is measure what happens to the surroundings. So if we can see what the surroundings do, they gained an energy, then the system had to give up some energy because of that law of conservation of energy. If the water gets warmer, then the energy content of the system had to go down. And that's the basics for all the calculations we're going to do from here on in. First, tomorrow, we're going to learn on how to deal with the surroundings. How do we do calculations on the surroundings? What happens if they warm up and if they cool down? And if you've taken grade 11 physics with Mr. Petrus, then you've done equations. I call it Q equals MC delta T, but he would have called it EH maybe, heat. Did he call it heat energy? MC delta T. Those are the exact calculations we're going to do tomorrow. You've done them if you've taken the physics. That allows us to calculate what's happening in the surroundings. Then we're going to look back at the system. What can we learn about the chemical system? That's really what we're interested in this course, chemistry, is what's the chemical system doing? Can we learn about that? So we've got to learn a little bit of physics about the surroundings, and then we'll apply it to chemical systems. Okay, so that's a perfect place for me to stop talking. If I can bring that up.